With a very warm wishes, I'm Nilesh Kumar. I am a PhD scholar in the Department of Mechanical Engineering, IIT Madras. So today I'll be giving a review on the paper crystallography orientation of refined grains by adding titanium and zirconium in aluminum through casting by Zhongwei ETA. So this topic is actually rephrased, and the actual topic is given in the description below with the DOI link. This paper was published in 2020 in Nature on Scientific Reports. So in this I'll be going through the introduction, what they have done actually, research methodology, reviews and their conclusions. So just a disclaimer that all the contents are from the given link and the given paper unless and until the reference is given. So we know well that casting is a very well-defined phenomena in which grain refinement is a subdomain where we aim to get the grain size as small as possible. So getting a small grain size has their own benefits, like the strength is high, the dislocation propagation gets very low because of the hurdles due to the grain boundaries and that. So there are multiple research done on which we find many methods to refine the grains. In this they have done the grain refined by titanium and zirconium in the aluminum melt, where it has been formed to Al3Ti and Al3Zr due to some oxidation in that. And this is a heterogeneous nucleation. So there are two kinds of nucleation in any casting for the process of solidification, that is homogeneous nucleation and heterogeneous nucleation. Homogeneous nucleation has a property to nucleate in the melt without any second state. For example, if a nucleation starts inside the melt and there is no other medium for that particular nucleation to start, for the particular embryo to start, so it's a homogeneous nucleation. But when it gets another medium, so the energy gets reduced for that another medium, and there the nucleation starts. So generally heterogeneous nucleation starts at the entire boundary of the casting shell, also known as the vessel or the crucible. So at that the energy is low, so there heterogeneous nucleation starts. So there we get refined grains. But we want more refined grains in the middle of the melt. For that we add some incoagulants known as titanium, zirconium and other things also there, to get some heterogeneous nucleation inside the melt in between the. So they have done the analysis through S2S matching, E2EM, and electron backscatter deflection. So EBSD is a well-defined parameter to get about the grain size, misorientations, and the different kinds of propagation in each grain. So since it's a broader topic again, I'll not be going on the EBSD. It's a well-defined topic. I may make some videos in future regarding the EBSD imaging. Here we will be talking very briefly about S2S matching because it's a new technique and it's not very well known, but still it has been used to predict the different kind of orientations from the crystal and the sample surface. So we'll be briefly talking about what is S2S matching. It was mainly given by Zhang and Kelly. It basically predicts the orientation relation for a given system. So when we talk about orientation relation, what it actually means? It means that, for example, if you are having two different phases, BCC and FCC. So on BCC, what is the angular orientation of FCC? That's it. That's only it is. So it's the relation between the specific plane and direction of two crystals on either side of the boundary. So it is basically depending on three parameters, or it is basically defined by three parameters. That is the crystal structures, that is either it is BCC, FCC, lattice parameters, or atom position, like where the atom is positioned there. So there are a few important assumptions that has to be taken care of while doing the E2S, E2E matching. So since it is predicting, so it's not done after processing, it's actually predicted before the processing. So the assumptions are the interface between the two planes must be coherent. As we can see, BC and FSC are coherent on each other. There can be some angular differentiation. There can be some angle difference, but it should be at least coherent partially or completely. And the main aim is to achieve with a very low surface energy, as we can see here. So this is the main requirement for E2EI matching, that it should have the as least energy as possible. So we can see, like in this picture, like there is like we can see, suppose that the white dots are aluminium. I'm talking, just give an example. The white dots are aluminium and the black dots are the new nuclear form. So we can see that this exactly at this part where it is showing good matching, it is like almost coherent on each other. But when we go to this part, I hope that my cursor is visible. If we go at this part, like where this black and white dots are separated, so we don't say that it's a good matching. So this is the one rule, that it should almost have a good matching region. Close pack atom. So we can see in this, this is just bottom of it, like it should be either parallel or it can be zigzag. So suppose, as I told, that this is the like we can sample crystal structure, and this is the grained crystal. So we see that both the things are almost like in parallel, or it can be zigzag in column wise, and they should also be effective spacing, like in the row wise, it should be on top of each other. So this is an ideal condition. So it is given by interatomic, given by FR. So there are two parameters here, as we discussed at the previous isotope, interatomic FR and the interplanar misfit. So these two parameters define like what is the E2A matching for it, given by this equation, that if there is, we are talking about this atom, then interatomic misfit, spacing misfit we take, that is FR given by RA minus RP by RP, where RM is actually the interatomic spacing of matching row of metal matrix, and the RP is about the incoclant of the same parameters. So here we are talking about the atoms only. In this paper they are talking about the atom mainly, and talking about the interplanar spacing misfit. They have talked about DM and DEM minus DP by DP, that is interplanar spacing of matching row of metal matrix and of the incoclants for the same parameters. So the thing is that how they have done, how this. So we talked about the introduction, what how things are going on in this paper and in which direction they are going. So we'll be discussing what are the experimental procedure for us, like how they have done actually. So they have taken a pure aluminum with 99.995 purity and they have melted at 720 degrees Celsius. So the melting point is about 660, but they have gone up to 720. Preheating temperature of the titanium and zirconium is 200 degrees Celsius. So they have actually preheated the entire incoclant. The mixing ratio they have taken was 4% of zirconium in aluminium and 4% of titanium in aluminium, and 0.1% and 0.2% respectively. So in this entire paper they have only talked about 0.1 and 0.2% mainly. So after that, what they have, like in testing parameter, what they have done the EBSD to understand the orientation of different grains. They have prepared the sample, like they have done the electropolishing, done at 30 volt at for 5 seconds to 15 seconds, and then they have used the SQL technology of software channel 5 for this. Like when we do the EBSD, we get the raw data to make it the actual data. They have used the software, this particular software they have used. So this is the main part, talking about the result, that what they have got. So that part A is actually as cast, or we can say pure aluminum, nothing is done here. So we can see what is the length of the grain, it is quite high. So when they have added 0.1% of titanium, so they have found a tremendous amount of grain refinement. We can see the difference in the picture of A and B. So we can see that there is a tremendous amount of grain refinement in both the comparison, we can say. For the testing, they have, for sensing for EBSD, they have used a step size of 50 micrometer because it is quite fine, and compared to the aluminum, they have taken 30 micrometer because it is quite large grain. Again, if they add 0.2% of titanium by weight in the aluminum matrix, they find that like more refinement is compared to 0.1% of titanium. So they have found that 0.2% is more effective. So I'll be discussing in later time what they have found. Now, when they add zirconium by 0.1%, grain refinement is there compared to pure aluminum, but is not as significant as they are adding titanium. And similarly, if they are increasing the amount of zirconium by 0.2%, it is more fine compared to 0.1% zirconium, but it is not very effective compared to even 1.1% of titanium. So, like they have concluded, zirconium is not a very good refinement compared to when it compared to titanium. So titanium is a very good refiner actually. So these are the conclusions that they have found, that good refining was done by 0.1% of zirconium. Large columnar grains were there with 0.1%, but in 0.1% titanium, very fine columnar grains were there. So the particle size by adding zirconium, they are getting about 1500 to 1200 micrometer. So this is the particle range that they are getting by adding 0.1% zirconium. But when they add even 0.1% titanium, they are getting 400 micrometers. So it is extremely less compared to zirconium when we see this. Just see the figures there. And the average grain size after complete refinement was 100 micrometer to 80 micrometer. So this is the EBSD result of EBSD and EDAX result, and figure A is actually the same result. We can see the white part is actually the incalculate settled in the aluminum matrix. B part is the EDAX. They have talked about the composition, like what ratio aluminum, what ratio titanium is there in a particular this area that they have done the scanning of the area. So EDAX is done by 3 or 4 methods. First one is point analysis, then line analysis, then area analysis, and then complete figure analysis. So complete figure means that A. We can see this figure A, this complete figure analysis is there. But in this they have done the area analysis for this particular contrast only. So C talks about the EBSD imaging of this zirconium, or this is zirconium is for F and C is for titanium. So where this actually implanted in the entire matrix they have talked about here. So on talking about the orientation, they are talking about, they have got about 3:1 ratio of aluminum, like 3 is the aluminum and 1:1 is the actually the incalculate. So we can see this percentage, 74.3% is 34% is aluminum and 25.6% is titanium. So it is approximately 3:1 in ratio, and in the same with zirconium and aluminum we can see. So they have find that Al3Ti, that is the incalculate, is actually in the middle of the matrix. So what I discussed earlier, that we want this grain refinement to be at the middle of the melt, so inside in middle of the entire melt. So they have found like, yeah, they are able to achieve Al3Ti in the middle of the melt. This is the requirement. Like grain refinement is in the like the entire volume of matrix is there. Matrix is basically the aluminum, and inside that we are not only having grain refinement at the surface of the where heat exchange is there, but also in the middle of it. So this is their achievement, like this is what they have reported here. So this lends credence to the idea that both Al3Ti and Al3Zeta molecules in the composition are nucleating substrate that causes the refinement of grain produced by adding titanium or zirconium component to raw aluminum, that is as cast. So they must process a suitable crystal arrangement. As I talked, like for it to be matching, at least it should be coherent on each other. Then only we can talk about like what is the equivalent prediction for that. So here what they have got, for example, so this is actually a pole figure of both ammonium and Al3Ti, and in this the right side we can see the pole diagram of aluminum as a matrix and Al3Zeta. So when we see like just see my cursor at here. So when we see about, there are 4 dimensions observed, 4 different orientation of crystal is observed here at 1:1 pole figure. So what they have done, they have found, first of all they took a sample like at 1:1, this is the pole figure that they are getting. So in Al3Ti, this kind of pole figure where we are getting, that is the question. Again I am repeating, so this kind of pole figure at 1:1, this particular structure where we are getting. So they found they are getting at 1:2. So see the figure A and B, A in the red and B in the green. So at this 1:1 is traced at this 112 pattern is traced at 112 in Al3 Ti particle. Similarly, for 110, so you can see these are some arrangement of crystals here. A similar thing we got on 021. So we can see from 112 to 112, some incoherency is there, but still some kind of they are almost similar. Like it's not very far away from 112. 112 is not very far away from 111. So also we can see when we observe this 110 and 021, the number, the population of one orientation is not exactly as in 021, because I told it is in the ratio of 3:1. Similarly, all 4 samples were tested, and all 4 samples in Al3 Ti and with aluminum pole figure, they have matched like this kind of arrangement where in which pole figure they are getting. So 4 samples were tested. Similarly, for zirconium, we can see that they have tested for 111. They have got this particular kind of arrangement here. So they found that where this kind of arrangement is there in Al3 Zeta. So they found it is almost here at 114. So except this 111, all other things are exactly coherent. Like this is 110, same thing they are getting at 110. This is 220, same thing getting at 220. This is 110, same thing getting at 110. So it is absolutely coherent, we can say, except about 111 in Zeta. But ZR is more coherent, but it is not a very good. It is not refining the grains very efficiently. So ZR is not very significant here, we can say, even though it is having a very coherence with the matrix. Whereas TI is not very much incoherence, but some incoherence is definitely there. But still, it is very good grain refinement. So what they have predicted, they have predicted the incoherency angle that I talked about. FD and FR, that is given by interplanar misfit and interatomic misfit. Actually, it's misfit only. So they are getting from one pole figure, they are getting the misfit is about 1.65%, and FR interatomic misfit is about 5%. So we can see some misfit is definitely there. Nothing is idle in this pole, but still it is not very high. So some incoherency is there that they have found. So this is the result that they are getting actually. It is similar to what they have predicted on the particular software. So it is exactly the same. You can see 110 and 110. It is both are parallel to each other. So this is what they are getting. So this percentage is almost similar. So we can say that good crystallographic orientation matching and low lattice mismatch, both of these conditions are beneficial to reduce the energy of heterogeneous nucleation and promote nucleation. So we know that heterogeneous nucleation occurs when it gets a site where low energy is there. So here we are getting low energy. That's why it is acting as a heterogeneous nucleation site. So this is a very important phenomena or a result that they are getting. Since the energy is very less, the incoherency energy is very less. That is why it is acting as a nucleating site, and it is having heterogeneous nucleation phenomena here. So this is the entire theme of the paper that they have got. So this is the experimental result that they are getting, exactly what they have predicted here, as I showed. So in just a short, I will be talking about the results that titanium and ZR elements are efficient grain refiner of commercial aluminum, and its alloys at 0.2%. Titanium has more tendency in grain refinement of aluminum than equal amount of ZR, or equal or even more amount of ZR actually. Al3 Ti particles in Al-Ti alloy and Al3 Zeta particles in Al-Zeta alloy acts as a heterogeneous nucleation force during fortification, alloy fortification. So we saw why it is getting, just because the incoherency is less, so energy between the particles is less. That's why it is acting as a heterogeneous nucleation site, and that's why we are getting grain refinement, efficient grain refinement. So the crystallography orientation relationship between Al3 Ti and aluminum definitely, and Al and Al3 Zeta from both EBSD and L2M matching are as what they have got. It is exactly what they have predicted from the software. So they are getting the same thing in the reality also. So thank you so much. This is the end of the video. I hope this review was enough to get a brief idea about the paper, and I will try to make more videos on this in future.